So before we go and talk about true error, what we need to figure out is that why do we need to talk about it? In numerical methods, you're going to get two sources of errors, which are going to come, which are called truncation error and round-off error. Truncation error is where you are approximating a formula, let's suppose, or maybe taking only a few terms of a series because you're truncating a mathematical procedure. While the round-off error is coming from approximating numbers. So those will be the sources of the error. So how do we, so we have to quantify those errors, right? And so what we need to figure out about errors is that, hey, errors are not good, and we need to figure out how much error we can live with. So the first thing which we have to do is we have to identify where the error is coming from, and that's something which you will see throughout the course in terms of whenever we discuss a numerical procedure. And then second thing is that, hey, we need to quantify the errors. So once we identify the errors, we got to quantify the errors, and this quantification of the errors comes in two forms. One is called true error, and the other one is called approximate error. Approximate error we'll discuss in a different segment, but in this segment we're going to focus our attention on true errors. And of course we understand that, hey, what we're going to do is that we will minimize the error as per our needs. So that's how we're going to go about dealing with errors. Now, many people might say that, hey, why do we need to, how can we calculate true errors? Because we are using numerical methods in the first place because either the exact values are not possible to find, or exact values will take a long time for us to find. So what is the benefit of true error? The benefit of true error here is that, hey, if you are developing a numerical method, let's suppose, and you want to test it out, you may have an exact value for some special cases, and that's how you're going to test it out and see that, hey, whether your numerical method program or your algorithm which you have developed is working or not. So let's go and concentrate on what the definition of the true error is, and see through an example, and you'll be able to figure out the other parts of the flow chart which is here in as you go through the course. So let's go and see how true error is defined. So true error is denoted by the symbol E sub t, uppercase E standing for error and this for t, and that is defined as true value minus the approximate value. Many times this true value here, which you are seeing here, is also going to be called the exact value. That means exactly the same thing. So whether it's a true value there or exact value there means the same thing. So it's just the difference between what is the exact value and what you're getting as the approximate value from our numerical methods. So that's the definition of true error, as simple as that. And in the next slide, we will look at an example to see how we can calculate a true error. So here is the example which we'll be taking. We are being given an approximate definition of the derivative of the function as follows. And then we are taking this function with a step size of 0.3 or the value of h. And we're going to find the approximate value of the derivative of the function at 2. We're going to find its true value and henceforth find the value of the true error. So our definition for the derivative of the function is given as f prime of x is approximately f of x plus h minus f of x divided by h. Our value of x is, we were trying to find the derivative of the function at 2. The step size h is given as 0.3, so that gives us f prime of 2 is approximately this. So that gives us that, hey, we have to calculate the value of the function at 2.3 and 2, and the difference has to be divided by 0.3. So now all we have to do is to substitute the value of the function at 2.3 and 2. Since our function is 7 e to the power 0.5x, so in this case it's 2.3 minus 0.5x, but in this case it's 2 divided by 0.3, and this value here gives us 10.263. So that's the approximate value of the function at 2. Now in order to find the exact value, what is f prime of 2? And we have to find the exact value. We start up with our knowledge of differential calculus. So f of x is given as 7 e to the power 0.5x. And we already know that from differential calculus that the derivative of c e to the power ax, for example, where c and a are constants, is nothing but c times a times e to the power ax. So both c and a are constants in this. So that's what we get from differential calculus. So we apply the same thing here. We have d by dx of 7 e to the power 0.5x. That will give us 7 times 0.5 e to the power 0.5x, and that gives us 3.5 e to the power 0.5x as the exact value of the derivative of the function. So f prime of x is 3.5 e to the power 0.5x. So hence we get f prime of 2 equal to 3.5 e to the power 0.5 x is 2, and that value turns out to be equal to 9.5140. So that's the exact value up to 5 significant digits here, and we in the earlier part we found out what the approximate value is. So here what we're going to do is we are being asked to calculate the true error. The true error will be true value minus approximate value, and the true value we found from part B, which is 9.5140. The approximate value found from the first part was 10.263. So if we take the 2 and subtract, we get minus 0.749 as our true error. And that's the end of this example here. But one of the things which you're going to see here is that we're getting a true error of minus 0.749. How do we know whether this true error is a small quantity or a large quantity? So for example, if f of x was given as 7 e to the power 0.5x, that's what was given in the example. Let's suppose instead we have f of x equal to 7 times 10 to the power minus 6 e to the power 0.5x. Let's suppose the previous example, the only thing which was changed was the function. Rather than being given as 7 e to the power 0.5x, it is given as 7 times 10 to the power minus 6 e to the power 0.5x. If we repeat the problem, the true error would be minus 0.749 times 10 to the power minus 6. So suddenly for the same problem, just with a different function, slightly different function in terms of the constant being 7 e to the power minus 6 rather than 7, we get a true error which seems to be a very small quantity. So same problem, but we find out that in one the number looks very small, in the other one the number looks reasonably large. So how do we distinguish between the two is what comes in the picture, because we have to figure out whether the numerical method is working properly or not. So we might be calculating true errors based for trying to figure that out. So what we do, we have to define something called relative true error. Because now what we're going to do is we're going to normalize our true error by saying that, hey, it is the true error divided by the true value. So this basically gives us a proportion of it, and the relative true error is denoted by epsilon of t. So we had true error which was denoted by e sub t. The relative true error is denoted by epsilon of t. So let's go and take an example, same example as we had before, and see, hey, what do we get as the relative true error? So here is the example which we are taking for the relative true error, same as the first example, but the only difference is that we are now asking for the relative true error as opposed to the true error in the case before. So this is pretty straightforward in this case because we will take the numbers from the previous example. We got true error as minus 0.749. That's from the previous example. We had the true value was also from the previous example was 9.5140. So what is the true error? The relative true error. The true error will be the true error divided by the true value, and that gives us minus 0.749 divided by 9.5140, and this number here is minus 0.078726. That's what we get as the relative true error. Now, one of the things which you have to think about is as follows. So what we have obtained so far is that the relative true error which we got was minus 0.078726. And sometimes people will say that, hey, give us this number, relative true error, in terms of percentages. What are you going to do then? Then in that case, all you're going to do is you're going to take the number and multiply by 100. That's all you have to do. And you'll get 7.8726%. So relative true error can be written as a fraction or as a percentage, and depending on how the question is asked. If it's not asked, then you can give the answer in either terms. But if it is asked to be given as a percentage, then you give it as a percentage. If it's not, if it is as a fraction, then you give it as a fraction, and that's how it'll work. Now let's also, sometimes what they will do is they will ask you to calculate absolute relative true error. So in that case, what are you going to do? In that case, you're simply going to take the absolute value of the relative true error. So in this case is that is just the positive, the magnitude of the number turns out to be this. Or if it is in terms of percentages, you will just write it as this. Now, that's all there is to it. Now, going back to the example which we were taking, we said, hey, the function given in the example was 7e to the power 0.5x. Now, instead, if the function was given as 7 times 10 to the power minus 6 e to the power 0.5x for the same example, what's going to happen is the true errors which you will get for this problem and for this function for the same problem, they'll be different. They'll differ by 10 to the power minus 6 magnitude. However, so far as the relative true errors are concerned, they will be the same. So that's the power of each of these quantities which are defined, whether you're defining true error or whether you're defining relative true error. So relative true error gives you the relative mechanism of seeing that, hey, how bad your error is. So that's the end of this segment.